Hello students, welcome you for the topic on photodetectors for optical fiber communication. Outline of the video, we'll be looking at the principles of photodetector, two types of photodetectors, PIN photodiode and APD photodiode. We'll have a comparison between PIN and APD with respect to signal to noise ratio. So what is the principle lying behind this photodetection? Photodetector uses a principle of input as a photon energy, optical light. The output is a electrical. So all our electronic components which works on electrical energy cannot directly function on an optical input. So we have this photodetectors to be installed in the receiver segment of a fiber optic communication system. This photodetector is capable of converting a photon light energy into a electrical energy. So how does this happen? We have basically a PN junction diode. In between PN junction diode, we are going to add an intrinsic layer which will perform a electrical field nature, which acts as a depletion layer. When an incident photon energy H into F is greater than the energy gap, it's a reverse process what we have it in LED. So if the incident photon is going to have a greater energy than the electrical band gap of this PN junction diode, the photons are absorbed. An electron and hole recombination takes place in the PN region. Under the influence of this electrical field in the intrinsic layer of a depletion layer of the PIN diode, this is capable of producing a applied electrons and holes to be swept across the drift region. So you can see the diagram over here. You have an incident photon. When this photon is entering into it, it takes into the energy HF is greater than the band gap energy. Electrons and holes are created, and once it enters the electrical field region, this electrons and hole is capable of drifting, which results in the flow of electrical current. And this is being taken across a load resistor, and the optical power absorbed is going to be incident power 1 minus R, 1 minus exponential alpha into D. R is the responsivity factor. You have a drifting taking place from your P layer to the N layer in terms of your intrinsic region. The responsivity, I told you R, the small r denotes the responsivity. So what is the photon current? You are converting in terms of a current parameter. Therefore, the photon current IPH is equal to Q into P by H into V. So number of photons you incident per second. Q is the charge of an electron. 1 minus R. R is the reflectivity air to semiconductor device. Reflectivity component. 1 minus exponential alpha D. This is the absorption occurring in the semiconductor. How to calculate the responsivity curve? Capital R. IPH by P naught. IPH is called the incident photocurrent from your last equation divided by optical incident power. The Q by HV 1 minus R 1 minus E alpha D. So this can be rewritten in terms of 1 by R into 1 minus E alpha D is called as neta E. Neta is called the efficiency factor of your photodetector. So external quantum efficiency neta is equal to IPH by Q P naught by HV. So internal quantum efficiency Ni is equal to Ne into 1 by R. So you can write down Ne. Ne is what? 1 minus R, 1 minus E power minus D. 1 minus R and 1 minus R will be cancelled off. Therefore, the internal efficiency quantum purely depends on E power exponential. That's why we see that it capable of decreasing. It drifts down from your P to N layer. The drifting occurs, and that's how we can calculate the internal and external quantum efficiency of the system. How does the PN diode look into it? The PIN diode We have two types of pin diode. One is made up of the material silicon pin diode. The next one is indium gallium arsenide pin diode. So depending upon the manufacturing thing, we can apply any one of your pin diodes in the photodetector components. So silicon dioxide, you have PIN. P and N forms the junction. I is the intrinsic semiconductor added at this juncture, which is slightly different from that of your P positive chemical composition. And your photon is incident on the pin region. Automatically the drifting occurs in the intrinsic depletion layer, and all the components are converted into electron and hole recombination, and the electrical current are being generated with the applied voltage. Okay, next we come for the indium gallium arsenide pin. Here the combination is 3 and 5 component, therefore you have a narrow depletion with a shorter transmit time. So your peak power is high in this indium gallium arsenide pin diode. You have an incident photon, we have pin, and the intrinsic region is made up of different combination of the indium gallium arsenide and phosphide region. According to that, we will obtain the optical power input and derive an electrical charge output. Now, each and everything depends upon how does the rise time and fall time occur into it. So how to calculate the bandwidth of the system? The output voltage across the load resistance when it is taken, and V out is equal to V naught by exponential T minus RC. Tau RC is called as the time constant. What is the rise time? Rise time can be calculated as TR ln of 9 TTR plus TRC. TRC is the time constant. TTR is called as the transit time, which can be calculated by d by Vd. Therefore, the bandwidth of the system is equal to 1 by 2 pi TTR plus TRC, the trade-off between quantum efficiency and the bandwidth. Then next we move on to the second type of photodetector. We call it as avalanche diode photodiode. We have P region, N region, in between is your intrinsic region, as you can clearly see. It is again a extension part of your pin diode. Pin diode in high electrical performance result in the impact ionization. So this is one of your drawback in pin diode. It has an impact ionization if the electrical voltage is of higher range. To avoid that, we go for the pin diode. Electron and hole ionization rates are almost equivalent. It will create a higher avalanche noise. So in your drifting part, what happens is when an electron and hole is being regenerated, that particular electron, whenever it is generated, is capable of injecting the other atoms in the region, and it is capable of regenerating one more the other. So it keeps on multiplying. You have a multiplication factor. You can find out it goes on, hits another, then again a recombination takes place. It produces energy, again it hits another electron, so that you will have multiple number of electrons and holes to be created. Each and every time the electrons and holes are being created, and at one particular time the multiplication output is being taken. So we have larger gain with product to be produced with a higher electrical field combination, and the electron ionization rate is also larger. We have a less avalanche noise. So with these three effects, we assume that for an high spectral output, we define to say that APD diodes perform in a very greater manner than the pin diodes because of its avalanche multiplication occurring in the depletion layer. The gain bandwidth product, it's higher, so gain is almost independent of the bandwidth. The gain bandwidth product has been calculated. GB is equal to alpha by beta n into TAV. What is n is the normalized bandwidth to be calculated by 1 by 3 to 2. TAV is called as the average transition time taken place for the electron and hole recombination. This is how you can look into your thing. APD region, P plus pi, P and P. This is the structure in which you can form your APD. So you have a P region, pi region, P and N plus region. Higher fields occur, lower intensity occur in your pi region. Electrons are drifted to P-N junction through impact ionization. Whereas the lower drifting pi region, there is no ionization. So with this, avalanche multiplication structure can occur. And these two PIN diodes and APD diodes are capable of creating a noise parameter. What are the different types of noise available? Since you have the components to made up of P-N junctions, two main parameters have to be discussed. One is short noise, the next one is the thermal noise, as we know. Short noise has been considered due to the electron and hole recombination pairs randomly generated due to the input of optical signal. This has been evaluated using Poisson statistics, and the total short noise has been calculated with respect to Q into IP by ID. IP is the photon current, I is the drift current occurring to the system, Q is the charge of an electron. The next type of noise is a thermal noise. It's a random motion of electrons in a conductive medium. It is modeled by Gaussian process, and the spectral density is being calculated with respect to Gaussian characteristics, and the total detector noise is going to be thermal noise has been calculated by 4 kTB by R. This thermal noise and short noise, we have discussed detailedly how to derive these values in communication theory paper. So total noise created in the system is going to be short noise plus thermal noise. So you are adding two terms. One is due to short noise. One is due to short noise. The other one is due to the short noise, and this is due to the thermal noise. And the total noise occurring in your system. Now we need to find out signal to noise ratio. Signal power divided by noise power. Signal power divided by noise power, which is taken from the previous slide. And therefore this is the output. Now if I want to configure in terms of individual components, thermal noise power is 4 kTB and short noise power will respect to be 2 QHF. This is how you are calculating the signal to noise ratio of a photodetectors. It can be related with the PIN receivers. If you want to calculate for APD receivers, we have to have a multiplication factor to be included. So that has been defined in capital M. All the other parameters will remain the same. Only one thing, we are going to add the avalanche multiplication region effect into it. Thank you.